Okay, welcome everybody to today's webinar on PTV Viswalk, specifically on options variants for routing pedestrians. So that level above the collision avoidance, evading of individual pedestrians. So making pedestrians walk from origin to destination, and yeah, the variants which exist for that to control that in Viswalk. I will start from scratch with a very simple model in first instance, building it up, and then go through the options which we have with partial routes and the dynamic potential step by step, all in very simple demo example models, so nothing complex today, just to touch each of the features once and to give you more or less complete idea of the options you have here. So first I need an area which will be used by the pedestrians to walk on. So with control right click, it's inserted, created. Okay. And then a second area where I will set them into the simulation later, a destination area, and an input where pedestrians are created, and the input volume should be 3,000 pedestrians per hour. And now a route telling pedestrians to walk from left to right. And let's offer the pedestrians a choice that potentially they could go turn left here, walk into this corridor where they don't see that the corridor ends, in fact, after some time. It's a dead end. Just to check, what does Viswalk do with such a situation where pedestrians could walk into a dead end, have to turn around, and then come back to walk to the destination. After all, it could be when they want to walk here from the left side to somewhere here on the right side. A real person could think, oh, it's too many people here on the way. I go here and I will arrive at the destination as well. If you don't know the location, that could happen. So let's see if it happens. Doesn't happen in 2D, it doesn't happen in 3D. So here the pedestrians obviously know, it appears they know the location and what is the shortest path. And that's the basic assumption. So if you do just a very simple minimalistic modeling, then the pedestrians walk according of, say, a paradigm of shortest path. So they try to walk on the shortest path from origin to destination, and the only thing that makes them deviate from the shortest path is other pedestrians, when they avoid them, when they avoid collisions, when they have to queue up in front of a bottleneck, whatever. Now, how to model that a certain share of pedestrians here walks into that corridor to the point where they see, oh, it's a dead end, and then they come back. And that's one way, a simple application of partial routes. I change here to the wireframe mode to see the areas which will be placed one over the other now. First thing is create an area here slightly upstream of, let's say, the intersection, and then a second area here, right where pedestrians would see, oh, it's a dead end, I should not proceed here. and then we make use of a partial route. So here, you see, with that option you change from static to partial, and we create a partial route decision on that area upstream of the decision point. That's all fine for our first application. And we create 2 of these partial routes, 1, 2, and the first one here has an intermediate destination on that additional area within the dead-end corridor. Now, let's say we want about 20% of the pedestrians to walk into the dead end and then turn around, and this can be set, this information, in the list of the partial route decisions with the partial routes as a secondary option, and then I set here a 2, and for the straight line without walking into the dead end, an 8. So we will have a 20%, 80% share of pedestrians utilizing the 2 options. So that's a way to model pedestrians who don't know exactly the place, the location, that you use partial routes, for example, to model pedestrians not walking on the straight path, the shortest path, but sometimes they go somewhere else astray and come back. I mean, that could be interpreted in a different way here. Assume we apply a small dwell time on that intermediate area here in the dead end, and we only have, let's say, men maybe deviating here. Then you could interpret it as a restroom where people go, spend some time and come back. Then if you model an airport, for example, and you see already here this partial route decision, or all partial route decisions are class dependent. Let's just do it as an example here. I create a class of men, so it's just here pedestrian type man, which is part of this class, and I set here that it's not for all pedestrians but just for the men, and that's now something we have to follow in 3 dimensions to verify that now it's really just men, 20% of the men who walk in here and come back. So I didn't apply the dwell time to really model a restroom, but the base message is clear here. The partial route decisions are class dependent, and that adds a lot of power to them for application to model very specific elements in certain cases of application. So obviously the partial route is active as soon as a pedestrian steps on the area where the partial route decision is located. If this would be not a partial route but a static route here, all pedestrians without exception, no chance to configure it otherwise, would ignore it and would continue their main route to the end. Only if at the final destination of the main route, so here on this area, if there is another static route decision, so one of these, then they might pick it up and follow it. But if it's on the way between origin and destination, pedestrians ignore all static routing decisions. Just the partial route decisions are considered, and the partial route decisions are also considered only if they lead back to the main route, which means to a destination or intermediate destination of the main route. So let's check that. So I'm moving the destination to this area here. And you see the destination point of the other partial route changes as well to the same area. So I'm going back, and it's hopping also. So it seems, and that's the case, all partial routes coming from one partial route decision have to end on the same area. And let's see what happens after I have moved the destinations here. Now the partial route decision is ignored by all pedestrians. Why is this? It doesn't lead back to the main route. Okay, the pedestrians pass by over this area here as well, but leading back to the main route means the dots, the destinations of the partial route have to be on an area where there is also a route location, a destination or an intermediate destination of the current static route of a particular pedestrian. This is a restriction. Why do we have this restriction? It's a restriction because in traffic planning, the OD matrix is an input into the simulation which we want also as an unmodified output. So we know the OD matrix and we want the simulation to reproduce the OD matrix. We don't want the simulation to make pedestrians walk to other destinations, that in the end the OD matrix which we have modeled as an input to the simulation is different as an output. And only if it is guaranteed that pedestrians who have chosen a route also arrive really at the destination of this route, only then the OD matrix is preserved. And with these restrictions that partial routes are only considered if they lead back to the main route, we can modify what pedestrians do on their way to the destination without changing the OD matrix. And to decide if it leads back to a static route, of course, all destinations of all partial routes belonging to one partial route decision have to be placed on the same area. So that's the reason. It's a domino effect of restrictions and that we are faced with here, and that's the reason for this restriction, that they all end on the same area. So let's increase this small example model a little bit to the right side. So I just pick up destination and enlarge it a little bit. Let's have here another area, a bit larger, and add some obstacles. And the static route which I had before should have now an intermediate destination here at about the region where pedestrians enter this new large area. So let's see what happens now. We have the pedestrians here. They again walk into the dead end because it's leading back to the destination, the partial route, and we see pedestrians following the shortest path through this door here. Let's watch it in 3D. Here you can see the obstacles now, the doors. And if I now increase the input volume, twice as many, we can see that by and by there is a jam which grows larger and larger in front of that small door. And after some time it looks a bit unrealistic. You know, there is this large door, and they utilize it only really very, very late. So what can we do about this situation? Making pedestrians a little bit smarter here, and making them utilize the wide door at the here upper side or left side for the pedestrians a bit earlier, when the jam is not that large already. So that's a second application for the partial routes. Let me just at first move the deviating part here, so the dead end partial route here, for a specific reason. And I can create now here such an area and create an area inside this wide door, which implies a longer way. And if I now place a partial route decision on this triangle area to the destination, and then via this area inside the wide door, we have the following effect. You see that as soon as pedestrians step on this triangle area here, they realize, oh, there is a partial route decision, and it holds for me because it leads back to my main route, and then they are first sent to the intermediate destination and then to the destination area here. And you see, in this way we can prevent that there is a very large jam occurring in front of this bottleneck here. So that's how it looks like. And this is reacting dynamically. If I go back again to a smaller input volume, you see that after some time, when the queue in front of the narrow door has resolved, there are only very, very few pedestrians who still walk through the wide door. If I go down to even lower volumes, after some time it's probably no one anymore who walks the detour. And that's quite positive in this way, because it's realistic that the fraction of pedestrians who utilize the detour depends heavily on the full volume and the ratio demand over capacity that we have. So note that this is a somehow totally different way to utilize the partial routes than before. In the first application with the detour into the dead end, there were really two options, so walking into the dead end or going straight on. And the area where the partial route decision is placed such that it is guaranteed that all pedestrians will walk over it. So it's really a decision. Here in the second application, the area is placed such that it's not guaranteed that all pedestrians step on the area, and then there's only one route, partial route, attached to this decision. So it's not really a decision, but what is made use of in this case is the fact that the partial route decision applies when a pedestrian steps on the area, and the question or the deciding element is, does a pedestrian step on it or does he not? But then it's a deterministic consequence which follows from it. So it's with the same function, with the same functionality, two quite different ways of application and two different scenarios which are modeled with it. And for this second type of application, I've prepared before another example, and that example is also part of the setup. So if you have installed Viswalk, or also a demo of Viswalk and Visim, you will find it on your hard disk together with the program with Viswalk. And you see here that the concept I've demonstrated to you before is here applied in just more complex scenario scene with these, let's say, ticket gates. And in this way, pedestrians can be made quickly to utilize even the remote door. And what really is the effect of this, I can demonstrate when I move away these areas where the partial route decisions are located. And let's just speed it up a little bit. And you see they really prefer now to use the closest door on the shortest path. Only the second one is used, but also quite rarely. And there is a large jam evolving here. So with the partial routes, pedestrians can be made to walk detours, although for each pedestrian at no point there is any other principle but the principle of the shortest path that the pedestrian operationally applies. But still, you can make them walk detours and walk on paths which are more earliest arrival, quickest path, higher walking speeds, and so on. So back to our main model. Or not to the main model, I have prepared another example for a very specific, or not very specific, but one more element of the partial routes, namely that pedestrians can be made to decide about which route to walk, not only in the moment that they walk onto the area where the route decision is located, but you can make them decide in each time step about the route. And if you combine that with the time interval functionality, you can do something like here, where you can imagine what you've modeled is that the door, which they used in the beginning, closes. Every pedestrian on the way to the door sees it, and some turn around, some just change a little bit their direction to utilize the other door. And that's done this way. So that's the partial route decision. You see here the partial routes, the partial route which goes straight on, and the partial route on the detour. If I double click on the partial route decision, you see that in the options there is this option, decision model, so which means at which time does a pedestrian decide which route to walk. It's either by default entering the area, or it is every time step, as long as the pedestrian is on the area where the partial route decision is located, and that's what is set here. Different to every other example I have today in the workshop, in the webinar. normally it's entering the area, but here it's every time step. And then what I have is time intervals. So there are 2 time intervals for the partial route decisions, from 0 to 100 and from 100 to the end. And for these time intervals, there is at first all pedestrians on the direct path, the shortest way here, and then in the second time interval they are meant to walk the detour. And if we start it a second time, you will see here in the simulation time that exactly at 100 seconds they redecide which way to walk. So here we are, and that's the effect. So a small option, a small variant, but it offers a whole new category of applications. So, but now back really to our main model. Now, if you don't want to make pedestrians decide if they utilize the white door or not by just stepping on this area, but let's say by the time it took other pedestrians before to walk these 2 routes, then there is another variant of partial routes, and that's travel time based. So what I do now is I also place such an area inside the direct path, and I add to the route decision here a route decision through the narrow door on the shortest path. And then I change here the route choice method from static to travel time, which brings up a whole lot of new options. And let's stick with best route and 90% and average of the last 10 pedestrians. So let's see what happens. We have our first pedestrian. In the beginning, pedestrians are sent on both routes to collect data. How long does it take to walk the path from the decision to the destination? And then afterwards, 90% are sent on that route which has the lower average travel time of the last 10 pedestrians who have arrived, who have concluded the partial route. And you see it's oscillating a little bit. So it's not really a distribution of pedestrians, because we have this decision model of 90% versus 10%, but that can be improved a bit if we go to lodge it and as a decision function and set here in the denominator 10. So it's e to the minus travel time by 10 seconds. And now we get a better distribution. Still, this problem, this method bears sometimes a problem, because it's by construction the effect can only become active after some time. First, we have to collect the data. How long did it take the pedestrians to walk the path? And then it can have an effect on pedestrians following. And sometimes that's too late. And when it's too late, in cases when it's too late, with all of these functions which you've seen, oscillations occur. So if we play around and have larger input, we might see it. But you see, nevertheless, although there is a bit of an oscillation, it's still quite a good distribution, and the extent of the queue here on the shortest path is limited. So also here, as before with the static route, when there were a higher fraction of pedestrians walking the wide door path, on the longer way when there was a higher demand. It's the same now with the travel time partial routes, that the fraction of pedestrians who are sent on the detour reacts dynamically and is increased when there is a higher total demand. But then there is a third variant of partial routes where the reaction on what's going on at the bottlenecks comes immediately, and that's density or quantity based partial routes. I will only present the density partial routes, but please keep in mind that there is also quantity based partial routes which are working exactly the same, except that it's not on density but quantity, number, how many pedestrians are there. So for that we need two additional areas in front of this door, also in front of this door, and then I need to open the list of pedestrian partial routes. And when I change here from travel time to density, let's stick with the logit model. And here for the lists, the secondary list of the partial routes, I choose pedestrian route choice areas. I activate the label display for the areas. And now I want to say, Viswalk, please consider this area number 13, the density here, for the volume of pedestrians who are sent on this route, which is highlighted now. And to do so, I need to select this route here, and then right-click in the list of pedestrian route choice areas here. So that's selected here. Then add, and it's here. I just select the ID of the area, and I do the same for the other route. So here it's area number 14. Fine. Let's see what happens. At first, pedestrians are sent with about equal probability on each of the two routes because there was zero density on both areas. But then you can see here dynamically the relative flows, so the probability for each pedestrians to be sent onto one of the two routes. And it depends and evolves with the density on area number 13, respectively area number 14 for both of the routes. That means, of course, the shape of these routes, 13 and 14, has to be reasonable. So that's crucial that you give these two areas a reasonable shape to also have a reasonable result for the relative flows. But if you do so, the density-based partial routes offer quite a powerful way, even more powerful, I think, than the travel time-based partial routes, to control pedestrians, what they do, where they walk, which routing variants they choose, and yeah. So you can use this for the density and the quantity-based partial routes. These have a property which is not there for any other route choice method in Viswalk, also not for the travel time based partial routes, nor for the dynamic potential, which I will show you later. If we make the dead end here not a dead end, but a corridor which is just connected also to the main hall here, and then I cut through here. So now pedestrians have to decide already here where they might not see what's going on in front of the second bottleneck here, if they walk the straight line or if they pass or go the other way through the former dead end. And to do so, I just take away the former dead end partial route and I change the position of the density-based partial route to this area. So let's see if this works and how it works. Yeah, pretty much the same. So the same is done as before. Density is measured on area number 13 and is linked with the route which goes here. Density is measured on area number 14 and is linked with the route which goes straight on. And pedestrians are routed accordingly. So now we can do one thing. We can just take out the area number 13. What will happen? There is now no pedestrian on area number 13. Density is 0, which means that more pedestrians than before will be sent on the route going through the wide door, because these pedestrians here, they imagine that the bottleneck here is empty, it's completely free. And we see this better if I have here a narrow bottleneck as well. And you see that here now a jam can evolve in front of the second bottleneck by and by. Because just so many pedestrians are going here because they think there is no one there. They don't see it at the moment where the decision is made. So that's a special property of the density and quantity-based partial routes, that the decision is, or the decisive element may be somewhere very, very remotely, located very remotely, not linked to the position of the route at all. So having somehow a remote effect. And we can do the opposite as well. If I place here a separate model with many pedestrians now walking over area number 13, so now the pedestrians who decide here think that here it must be quite crowded because they see there's already many people going here and more go straight on. So you can model with the density and quantity-based partial routes even what goes on in the minds of pedestrians, which they use to decide which route to walk. Okay, that's it with the partial routes for now. And now I'd like to show you that you can model the same utilizing the dynamic potential, and for that I just delete here the partial route, I delete this inflow input, and I delete the partial route decision here. And the only thing I need to do to activate the dynamic potential, first, we don't need this intermediate point here either. Let's first check how it looks like if we do nothing. So no dynamic potential, no partial route, and I mean, you can imagine it. Everyone is walking the shortest path, and a jam evolves in front of the narrow door which we have here, and it's building back, and after some time probably some pedestrians might be jammed to this point here. We can try to speed up with the quick mode, and then it can happen that at some time a pedestrian here is placed closer to the destination if walking here, and then the pedestrian will do so. So now it's happening. So that was the first guy who was just pushed back, and that for him the shorter path now is going here, but that's not really realistic. So what can we do to improve on that, except for partial routes? It's Alt, double click. I mean, you can also do all of this in lists, which is easier once you're experienced, but to have an imagination which options are available, which do I have to set, it's better to look at the dialogues, and therefore I'm doing all of this with the dialogues. And yeah, activating, inserting a dynamic potential is easy. After Alt, left, double click, use dynamic potential. Let's have as calculation ear interval 0.2 seconds. G a bit larger than normal, because we have to have quite some strength here that they really deviate. Let's stick with the H as it is, and yeah, that's fine. So quite easy to configure a dynamic potential, and then it looks like this. And as soon as we have a jam evolving here, pedestrians start deviating. It's much less work for modeling than the partial routes, but you see already that the simulation is a bit slower than before. So you have less work modeling, much easier, not so much to think about, not so much to worry about, just activating it and maybe the value of parameter G. But then Viswalk, the simulation, the computer has to do more work, more computation steps have to be done, and the simulation runs slower. Here it's pretty okay still. We have still a factor of 3, 4 even compared to real time. But if you had, let's say, 100 dynamic potentials, then it can become quite slow. You see that here pedestrians are a bit zigzagging, and that can be improved with a little bit more of computation time. So reduce the calculation interval to 0.1 seconds, and the cell size also to 10 centimeters, and then the zigzagging is gone, and they are walking smoother, but the simulation is a bit slower again. Also the value of parameter G, the 2.5, it's quite high, and that also makes pedestrians think really in every moment, oh, what would be faster, where could I go? So really being very aware what could be the quickest path, and that also produces a bit of this overtaking, what is the best path, left or right. If this is reduced, let's see the effect of parameter G to the default value, and therefore it's the default, because it's more of a typical situation, not highly aware of what's going on, but still reconsidering where to walk. Then it looks a bit calmer, what they're doing, not so nervous. And it also takes a bit longer before the first pedestrians really utilize the detour and walk the longer path. So that's for this parameter G a decision, a balance that has to be made. Good. So these examples were all on weighing, balancing shortest path versus earliest arrival, quickest path in a way. There is one more variant of partial routes which has nothing to do with that, but which is there to send pedestrians into a queuing system. And at the end of this webinar, I'd like to show this to you as well. So here's an area, a destination area, an input area. Let's go to the wireframe mode, enlarge, and here I create an area which I want to be a queuing area with time distribution number 1. What is time distribution number 1? It's the time distribution. You see it here with a mean value of 20 plus minus 2. So let's give it a name, 20 plus minus 2. And you see here, yes, it's the 20 plus minus 2 time distribution. And if I add a route, simple route, and an input, of, let's say, 400 pedestrians per hour, we see what happens is that they ignore the queue. Why do they ignore the queue? Yeah, we set the pedestrians with the route. We set them walk from left to right, but we didn't tell them to join the queue. To do so, we have to place an intermediate destination on the queuing area, and then they will join the queue. And there is a service time of these 20 plus minus 2 seconds for each pedestrian, and that's what they are waiting for, and then they continue and proceed with their way. But that's a simple single queue, especially or mainly or often at the immigration or at airports. You have such fork type queues. So there is one main queue, and then at when you're almost at the service desk, then it distributes on many smaller queues where people are processed in parallel, and that can be modeled using the partial routes for service points. So what I do is that I first multiply the queues here in the front, and then I create one here, and I change the routing point, the first one, to be on the central, the main queue later, and then I can add a partial route for service desks. That's done like this. So the first create the route decision, service point selection, and I want the pedestrians to proceed from the main queue to the forks in a way when there is no more than 3 pedestrians queuing there. So 1 being served and 3 more being queued, and then it's blocked. No one will join that queue furthermore. And we need 1 queue for each, or one partial route for each of the queues. And we see the following. Still now the pedestrians have a long reaction time here. the 20 plus minus 2 seconds, they are still applied, which is not really realistic. Sometimes it might be realistic to have some reaction time, that they're not proceeding immediately. So you can have a time distribution of 1 or 2 seconds or something like that, but 20 might be just too long. So I simply erase the time distribution for the main queue, and then we have a more realistic behavior. So you see they're distributing, and it's just not sufficiently many pedestrians to see the full system, the queue. So now we have a main queue with a higher input volume, and when I go down to smaller volumes, you see that it's processed, and you see the effect of that system. I can even say, okay, to model a cashier in a supermarket where there is no main queue but many parallel queues, where you can really choose where to go to, and there is no limit to the length of the parallel queues, then what you do is take the queuing away from this main area here, configure that it's not 3 people before you proceed, but let's say 999, just a very large number, and you can then just enlarge the area, and it looks like this. We need some more. So now there's a rush in the supermarket, and again fewer. So that's again just the same function, the same functionality applied with different parameters, and you can model a different situation. Not immigration at an airport, but checkout in a supermarket. This type of partial routes, the service desk partial routes, they have one special property which is different from other partial routes. Before I told you that whenever a pedestrian steps on an area where there is a partial route decision, where the routes lead back to the main route, the partial route decision applies, and there doesn't need to be an intermediate destination of the main route on the area where there is the route decision of the partial route. For the service desk partial route, there has to be an intermediate destination. Why is it like this? So you see they ignore it if there is no intermediate destination placed here. And if it is, they consider it. It is like this because if it's a queue, I told you before, to make pedestrians join a queue, there has to be an intermediate destination. And for that reason, because when it's modeled as a queue here, there has to be an intermediate destination. It's just the same rule applying here. If there is a queue on this area or no queue, it's just the same rule. There has to be an intermediate destination that the pedestrians consider the partial route. So you see, when it's a queue, it's quite natural that the pedestrians have to be sent to the point here, the tip of the queue. While when there is no queue, it doesn't seem so natural, but it's just we stick to the rule in the implementation that there has to be an intermediate destination. Okay, so that was it with modeling examples. I'd like to summarize now the difference or the properties of partial routes and dynamic potential and place the two side by side. The purpose for partial routes and dynamic potential in principle is basically it's the same, to make pedestrians deviate locally from the shortest path. But for partial routes there is some more specific applications. Partial routes can be used to model the will for early arrival, just as it is the case for the dynamic potential. But partial routes can be used in addition to model certain tasks, like aligning in a queue at a counter or a ticket machine, going to restrooms, and you can use partial routes to model unfamiliarity with the environment, walking into dead ends, and so on. There are more purposes in more complex models, which I could not discuss today, as it takes much more time, and I'm already with 1 hour here. Partial routes are spatially discrete, both concerning decision, also concerning the effect. So the partial route decision is on an area which has a discrete boundary, and it's sending pedestrians to areas with discrete boundaries, while the dynamic potential is continuous, both in effect as well as in decision. Partial routes apply, or the decision at partial routes on where to walk is done at certain times only. It's a bit limited, this claim now, that we have the decide every time step, but it's still true in the sense that the decisions are limited to the times when the pedestrian is located on the area with the decision. While for the dynamic potential, the decision is made in each time step until a pedestrian has reached this destination or intermediate destination where the dynamic potential is active. Partial routes and dynamic potential both preserve the OD matrix, so it's both just local rerouting. For partial routes, the effect most of the time for most partial routes is along the route, but it can also be remote. I've shown an example to you where the effect was remote when I modeled what's going on in the imagination of pedestrians and not what really happened. For the dynamic potential, it's always the effect along the route which is used to route the pedestrian. So there is not really, in a sense, a remote effect that comes from a totally other part of the city or from imagination. It's always somehow real. What enters as a cause, the dynamic potential, where then the effect is computed. The modeling effort for partial routes can be very small, but you can use it also to create really complex decision schemes. You can use partial routes where otherwise you would need maybe a scripting solution. So it can be somehow quite arduous, but that's related to what I've written here. The flexibility of partial routes is quite high. The modeling effect for dynamic potential is always negligible. You just have to activate it. The flexibility, therefore, is moderate. So it's pretty clear what's going on, and the situations which you can model and have an effect on with the dynamic potential, it's quite clear. It's always the same. The additional computational effort for partial routes is negligible. You won't really realize that the simulation is running slower, while when you use the dynamic potential in large models with large areas and you have many dynamic potentials, you will see that the simulation runs considerably slower. Then, just some alternative descriptions for dynamic potential, because the word dynamic potential doesn't really produce an imagination what it is. But there are alternative descriptions like map of time to arrival, earliest arrival movement paradigm, or quickest path movement paradigm, as you could also say, or even one-shot assignment, which describe a bit clearer what the dynamic potential does. If you want more information on the dynamic potential, more examples, what it does, what is its effect in certain situations, you can go to these YouTube videos in our YouTube channel at PTV Vision at YouTube. I just give you the time to note these links, so just write down these letters here so that we have two videos which show the effect. And also have a look at the description here below the video, which explains for all of the scenarios what's going on. And if you want to read papers on it, so not visual content but math, you can have a check for these papers here. So it's not a black box, the dynamic potential, but the method is documented fully, publicly, and the access is free to these papers. So that's it. Thank you for listening. Thank you for joining the webinar. I will now end the presentation, but I will stay in the chat and answer your questions. Please be a little bit patient if I do not answer your question immediately. As if there are many questions, it may just take some time before I come to your question, and so it will be written. So please write your questions and I will answer in a written way. So thank you and goodbye.